Hi kidlets, this is your first lecture for stellar evolution, sun-like stars, massive stars, death of stars, and black holes. So if you were taking notes, which by the way for this unit are going to be worth 30 points if you choose to take them, this would be a good outline, and I'm sorry it gets all functified when I upload. So this guy should be your number 1. This is letter A. So evolution of a sun-like star, death of a low mass star should be number 2. And then you have A and B, and then you have fate of Earth underneath that. So we've already talked about hydrostatic equilibrium, which is why all stars are stable on the main sequence, where you have this outward pressure of fusion, which is exactly balanced with all the weight of the layers above the star and the gravity pushing in. And this is why stars are stable on the main sequence. But there is this time in a star's life when it leaves the main sequence. And from then on, it totally depends on the mass of the star. And we've already talked about how the mass determines where it falls on the main sequence. So when you have a low mass star, it dies very quietly. And high mass stars go out with a bang. So the mass of the star not only determines where it falls on the main sequence, but it also dramatically determines what sort of death it has. So even while stars are on the main sequence, they're also changing. So if we look over here, we can think about this as being the center of the star, and here is moving away from the center of the star. And here would be when the star is born. And you can see that there is a much greater proportion of hydrogen than helium. So even internally, even when it's stable, there is this internal compositional change that's happening. So fusion, as we know, happens at the core of the star. So it's the core of the star that is beginning to change. So at the core of the star, you're gradually becoming hydrogen deficient as the core of the star becomes very helium-filled, and fusion begins to move away from the core. So we can see if we look down here at 5 billion years, we've got a pretty even mix in the core of the star, but then after 10 billion years, it's very hydrogen depleted. And during this time, the core also becomes larger. So once all of the hydrogen within the core has been depleted, fusion begins to move outwards. And you begin fusing then your next element, which is helium. And for this to happen, you have to have greater than 100 Kelvin. It should be 100,000 Kelvin. And you begin to have your core cooling, and you begin to have burning that happens away from the core. When this happens, the star is in the red giant phase. So you have this expansion, but the core of the star is also cooling. So it's very luminous because it's large, but the temperature is actually cooling. So here would be what the internal structure of a star moving off of the main sequence would look like. So you have this hydrogen burning shell. We end up with this helium ash in the center. And this part out here has not been incorporated yet. Fusion has not hit this non-burning envelope. Next slide. So how that would look on the HR diagram is here's our main sequence, as we've already discussed. And when it moves off of the main sequence, so say like a sun-like star that was right in here, it would begin moving laterally and then up. So you can see that the temperature, because temperature is decreasing to the right, our temperature is going to decrease as the star moves up here. But its luminosity is increasing because remember, these are lines of radius. So you have an increase in radius and a decrease in temp. So this would be, and obviously this is an artist's rendition, but of what sunrise in 5 billion years or so could look like. And it's unsure whether or not that it would actually overtake the orbit of Earth. We know that it would overtake the orbit of Mercury and Venus when it's in the red giant phase. So helium fusion is specific only to sun-like stars, and this is what really marks the end of the red giant phase. The helium fusion, or the helium flash, is essentially a runaway rapid explosion where the star is drastically trying to maintain equilibrium again. And when this is done, you're left with a hydrogen-burning shell and a helium-burning shell. But the star is moving laterally across the HR diagram, so it's not increasing in luminosity. But this phase marks the end of the red giant branch. So on the HR diagram, your star, which here is our main sequence star, which has moved up to the red giant branch, when it's in the helium flash, it then begins to move this way. So here you can see we have this non-burning envelope because this part still hasn't been touched by fusion because fusion is gradually moving out. And we're left with a hydrogen-burning shell, and then in the interior of the star, a helium-burning shell, but now we have carbon ash on the inside because a sun-like star can burn beyond helium to carbon. So if we were to look at the core of a red giant star, here would be our core, this would be the sun today, we can see that we've got hydrogen at our core. If we look, and this is the radius of the core of the star would be a 1/100th of an AU, which is pretty small, and then a red giant core would end up with a helium burning shell surrounded by helium and carbon. So that's the main difference between a sun-like star and a massive star, is you develop a carbon core here, and it can't fuse anything beyond carbon and then a little bit of oxygen as well. So here we can see we have a flow chart of the evolution of a sun-like star. So here's our protostar going this way. So here we have a main sequence G-type star, very convenient, it's just like ours. So here is this main sequence branch. You can see we have this sun-like star that exists like that for the majority of its life, continuing down here. And then when it begins to burn helium and then eventually carbon at its core, we get our red giant. You can see it's gone from yellow to now orange, so it's cooling. And then when there's nothing left to burn, we're left with a white dwarf, which eventually just fades away. So we need 600 million Kelvin for fusion past carbon, and these stars just do not have the mass in order to fuse those. So this is essentially where a sun-like star, this is where our star will stop. But before it becomes a white dwarf, we have this beautiful phase, which are some of the prettiest things in the universe, called a planetary nebula, and no two are alike. So when it's in this phase, there's no more outward fusion pressure being generated, and the core is beginning to contract. So right in here, you can see all of the arrows are pointing to the core of the star. This is what our sun will eventually be. But you have these extreme solar winds that are blowing away all of these outer layers, thousands of miles per hour, that are expanding and blowing away, expelling all of these outer layers into space. So these are beginning to expand, and the planetary nebula phase, like the Helix Nebula right here, which if you look online is also called the Eye of God, because it looks like an eye of God, these can be bigger than the solar system. So you can have this tiny core of the star, which can be smaller than Earth, and this envelope that expands beyond the solar system. So the star now essentially has two parts. We've got this carbon core and we've got this very large envelope. So I put in these other planetary nebulas just because they're so pretty. I wanted you to see them. So we have the Egg Nebula, Cat's Eye, brilliant names for NGC 5307. And then eventually, once that outer envelope has been expelled, we're left with a white dwarf. And a white dwarf is just that completely carbon and oxygen core. And these are extremely dense. So if you had a teaspoon of it, it would weigh 16 tons. And here's a little animation kind of showing you that. So white dwarfs can only be up to 1.4 solar masses, and that number is important. But they're very, very hot. Sorry, there's my kid. They're extremely hot, so they're 25,000 Kelvin. So they're luminous, kind of, because they're hot, but they're also very, very small. So here's essentially the way a sun-like star would follow on the HR diagram. So a sun-like star would start here, and it's basically doing a backflip, and it would end down here, and then the phase down here would be a black dwarf. As you already saw in your HR diagram, the black dwarf would just be white dwarf moving laterally over here as it cools off. So I asked you, once the nebula is gone, the core is hot and dense, but it's small, so is it luminous? So it's down here, so you know it can be very, very hot. But it's below this radii line, so you know it's not very big. So our luminosity is increasing up here. So because of its size, even though it's hot, it's not big. So this is one of our anomalies. And then our black dwarf stage is when there is no more luminosity or heat whatsoever. So here's one of our close by stars. This is a binary system. We have Sirius A and Sirius B. The small star is a white dwarf companion to a larger star, Sirius A. And Sirius B is much more dense than anything in our solar system. So here's a little size comparison. So there's Earth, a solar mass white dwarf, and here we'll talk about neutron stars, which are smaller, but the most dense thing known to exist. And I said earlier how white dwarfs can exist past the 1.4 solar masses, and that number is really important. It's called the Chandrasekhar limit. And there was a student back in the 60s, he was hardly older than you guys, and he discovered that beyond this mass, white dwarfs are incredibly unstable. So they have to be smaller than 1.4, and this happened to be his last name. It's also who the Chandra telescope was named after. So here we can see that Hubble has imaged many white dwarfs in these globular clusters. As I mentioned last unit, the universe is not old enough to support black dwarfs, because remember, these are low-mass stars that live long lifetimes. So there are no white dwarfs, we think, that have actually cooled off enough to be black dwarfs, because the first stars were all very massive and ended in supernova explosions. So these would all be pretty young white dwarfs. So this is what prevents, the Pauli exclusion principle is what prevents white dwarfs from exceeding that Chandrasekhar limit. So this prevents the electrons in the core from being crushed any closer together. So they're compressed as tightly as they can possibly be. And this pressure is resisting the force of gravity, and that's what's making it in equilibrium at 1.4 solar masses. So this is just stating that the electrons are as tight as they can be. They can't be compressed anymore. So usually in a single star system, a white dwarf is the end of the line. However, if a white dwarf happens to have a companion star, the white dwarf stage is not necessarily the end of the road. So if that binary companion happens to be a main sequence star or a giant star, or any star that has a greater mass than it can essentially have a gravitational field, because remember that this is a very dense object, and pull matter, the hydrogen and helium from the surface of the companion. As it's pulling it towards it, it forms an accretion disk around it. So you end up getting this mass transfer system. So if you follow along in this diagram here, so star B is more massive than star A, but star A is pulling material, so this is mass transfer. So where you have here, you essentially have the same size star, and these are your gravitational Lagrangian points right here. So these are important when we talk about like asteroids too. So by the time you get down here, you've got your white dwarf star, which is bigger than your giant star. And this really fooled astronomers for a long time because their rotations didn't match what they should have been. So this can affect their stellar evolution, and this is where that Chandrasekhar limit really comes in. So that mass transfer is really important in incorporating the Chandrasekhar limit, because a white dwarf star, once it is accreted mass that makes it greater than 1.4 solar masses, is no longer stable. That's called a nova, and we will talk about that more next time. But essentially, I mean, remember that we would not be here if we didn't have our sun. So the sun is eventually going to expand to a red giant in about 5 billion years. We got a long time. It could expand to Earth's radius, possibly Mars. Earth will be incinerated. Sun may form a planetary nebula. Some stars don't. We're not sure why. The carbon-oxygen core will become a white dwarf. It's no possibility of it becoming a nova because it is not in a binary pair whatsoever. So that is the end of your notes, guys. You will be having a notes quiz on this section next Monday. There will be one tiny little section I will be adding in on nova, and we'll go over this in class on Thursday as well.